Um, okay, let us start our seminar. Today we are glad to welcome Nils Albin Nilsson. He is a senior researcher at Institute for Basic Science, and he will tell us about gravitational waves and vacuum solutions with space-time-symmetry breaking. So please, Albin.
Okay, thanks very much for the introduction and the invitation. So I will tell you a little bit about a very exciting field of research, in my opinion, and some recent results in gravitational wave observables and, if I have time, some vacuum solutions that we recently derived. Okay, so very briefly, let me just introduce what I'm going to tell you. Although I doubt that anybody in the audience needs it, we're going to summarize general relativity in one slide. And then I'll describe what spacetime symmetries are, and then how I can break them in a way that makes sense. And then some consequences for gravitational waves and gravitational wave astronomy. So first of all, GR is a geometrical theory, depending on who you ask. And so the fundamental degree of freedom is the metric. And inside the metric, we have geometry, which is on one side, the left side, and you have some matter source on the right side. And you have associated with this a conservation law, which is the Bianchi identity, and a number of space-time symmetries. So first of all, you have local event symmetry. These are 6 rotations, which act in local event space. And then you have diffeomorphism symmetry, which are 4 translations, and they act on the planet. And these are related, but act in different space. So, this is my starting point. And then, let me describe in a little bit more detail what spacetime symmetries are. And I claim here that you can study spacetime symmetries in a theoretically motivated way, and also in a somewhat theoretic manner, using effective theory. So it was discovered in 1989 that you can have some solutions coming from string field theory which permit spontaneous local Lorentz violation. And then these things are also not predicted but not forbidden by some approaches to loop quantum gravity. And further, Hojawa in 2009 decided to break local Lorentz symmetry in order to obtain a renormalizable gravity action by introducing higher order spatial derivative and therefore a preferred frame in space-time. We are also interested in space-time symmetries because we can test space-time symmetries in a very precise way through conservation laws. So we can relatively easily write down a conservation law, and we can place very precise bounds on any deviations from said conservation law. For example, diffeomorphism symmetry related to the Bianchi identities or the equivalence principle and so on. And then there are a whole host of things that come out of various other approaches to quantum gravity. For example, non-commutative geometry, which can be directly related to local Lorentz violation, extra dimensions, and so on. But most of all, I think we base all of our modern physics on space-time symmetries. So really, we should be testing them. And we should know the cutoff scale at which this EFT construct, that is the standard model, hold. Okay, so we do this in an EFT sense, by which I mean that I have some cartoon of the universe, and then I break one of these columns as generically as I possibly can, and then I check what the consequences are for GR, for atomic physics, Newtonian gravity, and so on. Okay, so in order to do this, we need two different pictures of general relativity. Here, I'm only interested in the gravity sector, so we're going to stick to GR and its direction. First of all, the manifold picture, which is where the metric lives, which is where curvature tensors live. And then I can connect this to the local Lorentz space through the Vierbein, the orthonormal tetrads, which I have to do if I want to include spinors in my space-time. And it's in this local Lorentz space where local Lorentz transformations act. Okay. Then you have two different types of space-time symmetric transformations that you need to be aware of. First of all, you have local Lorentz transformations. These act in a local Lorentz space, and space-time points and tensor fields are observed, and you don't change the local basis. So the metric is unchanged, coordinates are unchanged, but the Vierbein transforms because it has local Lorentz indices. Okay. And then diffeomorphism transformations, by contrast, act by moving space-time points. So this has to act on the manifold. And this looks deceptively like a coordinate transformation. However, it is not the same. By which I mean that this looks a lot like a coordinate transformation. However, we evaluate these in the same space point through the Lie grid. Okay. Now, in traditional physics that we love in textbooks, there are two notions of transformations. There are active and passive transformations. And normally, these two are inverses of each other. It doesn't matter which one you do, whether you rotate your observer or you rotate your experiment. However, when one or the space-time symmetries is broken, this no longer holds. In fact, if I have a static vector field pointing in some direction, and I do an active transformation, I will also transform this vector field. And if I do that with a static background vector field, like I said, then I obtain unphysical results, such as server-dependent physics. So I measure something in Cartesian coordinates, somebody else measures something in spherical coordinates, and we obtain different results. And this we cannot accept, so on. So we have to generalize the type of transformations that we allow. They are exactly the observer and transformation. So observer transformation is exactly a passive transformation. You rotate your rods and clocks, you rotate coordinates, but you do not change any dynamic field. Particle transformations is a generalization of an active transformation, where coordinates are not changed, but you change physical quantity. However, any static background tensor that breaks a space-time symmetry is not a dynamical field, not the physical quantity, and so it does not transform on the particle transformation. And this will give you exactly physical local Lorentz violation, physical diffeomorphism violation. Okay. Furthermore, there are two ways you can break symmetries. You can break them spontaneously or explicitly. When you break something explicitly, you simply place by hand some extra term in the action that has certain symmetry properties. It does not have equation for motion. It cannot be on shell. There are no fluctuations around its background. And if you do this in curved spacetime, you are penalized with having to solve a conservation equation of this type. And as you can see in a generic spacetime, this is impossible. And this is what we call the no-go theorem. However, it was long thought that this was impossible in general, but as we've shown in recent years, this can be done in very specific situations, in very highly symmetric spacetime. By contrast, you have spontaneous spacetime-symmetry breaking, and this is much more familiar to most physicists, where you have some dynamic electric field that collapses into some VEV that's non-zero, and the VEV, the vacuum expectation value, breaks the symmetry. Here on the left is a simple example called the bumblebee model. You may have seen some papers on this. It's been very popular in the last 5 years. You have some extra vector field that breaks the symmetry through some potential. And actually, specifically for the bumblebee model, the number Goldstone modes here are exactly axial gauge photon. And this has received a lot of attention, specifically for black hole solutions. Okay, so this is the general picture, and I can briefly classify these possible types of symmetry breaking. You can find this in this great paper, 2021, where you can see, for example, that local Lorentz invariance and diffeomorphism invariance. An example is GR and its extensions. But for example, if I want spontaneous local Lorentz violation, diffeomorphism invariance, there's no physical way to do that. And so we have this general classification scheme, and as you can see, there are many options. So the question is whether I can do this in some EFT sense, in some general framework. The answer is yes, I can. This was worked out in the late 1980s. We call it the standard model extension. It was gravity is a relatively new addition to the standard model extension, only 20 years old. And originally this was the standard model of particle physics extension. And so we also have CPT symmetry breaking in here, which is of course connected to the local Lorentz symmetry breaking. And in the gravity sector, the corrections GR look like this. This is the derivative expansion to mass dimension 4 correction, so the lowest order correction. And this coefficient here, K, this is what you will go and place bounds on from an experiment. And in here, of course, you have to have 20 degrees, just like the Riemann tensor. And what's important about this is that physics is observer invariant in this context. You will not measure different results when you change coordinates or when you boost your observer. So let us write out the pure gravity sector, which is what I care about in this talk. And you can see here that as you move up in mass dimension, this, for example, is mass dimension 5, and here I have 60 independent components to bound or to constrain the experiment. And at mass dimension 6, I have over 200. And here I have not yet chosen this guy, which is any, and this L prime specifies the model. This is the dynamical terms, kinetic terms, potential terms, interaction terms. And so if I really want to find a strong gravity model, I need to pick some way to represent this EFT. And then I need to somehow constrain this with some experiment. And one of those very good ways to constrain spatial symmetry is gravitational wave. And I claim here that they are very sensitive probes of space-time-symmetry. So with the action that I just showed you on the previous slide, let me go to linearised-gravity. Now, if I want to write a quadratic correction to GR in terms of the metric potentials, then it can be shown that with local Lorentz breaking terms, my only option is this. So here is some generic quadratic correction to the action. H is the metric perturbation or metric potential, and K is some derivative operator. And you can show that there are 13 classes of such operators that you can write down, but only these three, I will show you what they are, but only these three survive if you also want to retain the linearized gauge symmetry of GR. So harmonic gauge, basically. If I want that, and we normally do, then I have these three options. And these three, S, Q, and K, are some derivative operators with some arbitrary number of partial derivatives attached. And now here I have some constants. These are constant tensors, coefficient tensors, and these are what I will place bounds on with my gravitational. They have some very complicated index symmetries. As you can see, as you move up in mass dimension, the number of indices proliferate, and you can describe this exactly with these Young tableau, like this, and it gets to the point where we had to write a whole Mathematica package to deal with these symmetries. It will come out pretty soon. So what happens to for example, the dispersion relation of gravitational wave? Well, up to mass dimension 6, you can write it like this. So yeah, this is GR, and then these zetas in blue here are some correction. And normally we write this in spherical basis with spin weighted spherical harmonics. And you can see here that this is a dispersion term, and this will give you, for odd mass dimension 5, 7, and so on, this will give you birefringence of gravitational wave. And so depending on the number of helicities you have, you can have up to 6 gravitational wave polarisations, and they can all have birefringence. And then you have some heptafringence type. Okay, and some collaborators of mine put this to use in LIGO with LIGO data not that long ago, and I'll just flash this. Here on the x-axis, you have one of these coefficients, exactly for mass dimension 5. And here is the PDF of these events, and there are some here, for example, this one in green, that seems to prefer a non-zero value of this kb. And we don't really know what this means yet, because this seems to indicate that this event prefers some mass dimension 5 local events violation. We have very similar results from the CMB, although I won't tell you about that today, where we also find quite strong hints of non-zero preference for non-zero coefficient. But again, it's not something that is agreed upon. And in the data tables, which we curate, then all the data still prefers local Lorentz symmetry. So Lorentz symmetry is still an exact symmetry. But I can show you some of the bounds that we have. So in this little table, you can find all of this in this paper. We update this every year, and right now you have Yeah, it's over 150 pages of constraint. So from gravitational waves, normally what we're seeing is constraints on the order of 10 to the minus 13. Right, so this is quite strong. And for example, in the solar system, using solar system test, we know that GR holds to 1 part in 100 million. On the other hand, from cosmic rays, you can find that the best constraint is on the order of 10 to the minus 66 GeV to the minus. Yeah, this is just a different coefficient. But the result is the same. Local Lorentz symmetry, as far as we know, is a very exact symmetry. Okay, so let me tell you a little bit about how to generate gravitational waves. Here I'm just talking about propagation of gravitational waves, but I also need some way to generate them. And this is specifically generating gravitational waves for the LISA mission for very weak binaries in the Milky Way galaxy, which is something that I've been worked on for a while last year. So the LISA mission will fly in space in about 10 years, and it'll be a triangular gravitational wave observatory with an arm length of over 2 million kilometers. So it will be sensitive to very low frequency and low amplitude gravitational waves. And in the galaxy, there are about 25,000 galactic binaries. These are white dwarf binaries with an orbital period of hours or days. So they're not coalescing objects. They're just sitting there orbiting slowly in spiral. And what's good about these objects is that they will be visible to LISA in the entire lifetime of the mission, which is on paper about 4 years' time. And this blue cloud here, well above the sensitivity curve of LISA, is galactic binaries. They're distributed in this way across the galaxy according to Gaia and simulations, and we have over something like 25,000 objects. And each of those 25,000 objects will be visible for some 10 to the 6 orbits of LISA. Of course, these do not come close to energy levels of coalescing black holes, but in return, we will have a big amount of data, very big amount of data. So how would I go about testing local Lorentz symmetry with these objects? Well, first of all, they're local, very local in the galaxy, and so I don't have to care about cosmology at all. So the Hubble constant is just a constant. The scale factor is always equal to 1, and instead I have to generate these corrections through exactly the two-body problem. So really, we're solving the two-body problem. And I need a source, as I mentioned. I have a source. It's a galactic binary. And it turns out that using this quadratic action that I showed you, and now I'll show you some more details, I can write the resulting Einstein equation in this way. And from now on, everything in blue is going to be GR, and everything in red is going to be some correction from symmetry breaking. And I wonder if I can do this. Okay, no. This capital M here is a long collection of these derivative operators. It contains an n number of partial derivatives. So what we did in this paper is I tried solving these equations in this way, an order by order way. And if you do this, and because the GR solution is relatively trivial, you find that you can apply a harmonic gauge at both orders. This is great. And in the end, you have to solve this coupled set of equations. And this is already non-trivial. Why? Because this H0 here is the GR solution. And when you solve this inverse Green function problem, what you end up with is some retarded solution. And so I have a box on the left side and a retarded solution on the right. Now this is going to give me issue. And if I write this out, just a formal solution, right, this I can do immediately. This is almost like a loop integral, but for gravitational waves somehow. So instead, we want to solve this in the post-Newtonian sense. I do some post-Newtonian, post-Minkowskian expansion. And when I do that, I have to choose the integration regions very carefully on the past light. So let me illustrate a little bit what that means. For GR here in this expression, I have some source here. Now this source has compact support. It's well defined. It's compact support in space-time. And so solving this using the retarded Green's function is relatively trivial. This is the past light cone. The source is sitting here in what we call the near zone. And the rest of the past light cone is called the wave zone, far away from the source. And your detector is sitting here at x. And so normally we split the integration. You do some appropriate expansions in the near zone, some appropriate expansions in the wave zone, and then you do some matching procedure on this boundary. Okay. Now this is perfectly fine when you have a compact source. But if I go back one slide, this is a compact source, but H0 is valid on the whole past light cone. And so the source that's now sitting here is no longer compact. It's valid outside the near zone of the source tau nu. And so actually I have to integrate this over 4 different regions depending on where I put the source point, which is the source, and the field point, which is where I evaluate the source. So this is enough details, but basically you have to solve these types of integrals. It gets a little bit messy, and all of this has to be regularized and so on. And we only provided explicit solutions for a very simple case where we could do this by hand. So in the end, what you have is some expansion like this. This is an expansion in the wave zone in terms of the retarded time tau. And what we found here is in GR there's no monopole correction, monopole contribution. There's no dipole. But here you do have a dipole. So breaking local Lorentz symmetry gives you a dipole gravitational waves. So if I want to show you a solution that fits on one slide, then I have to very carefully manicure this term to be something super simple that I can evaluate by hand. And this is what I did, which is in this paper. And it looks like this. Now, it doesn't really matter what I chose. The important thing here is that you have some very desirable features. It's a correction to GR, right? It has the right dimensions, and it goes as 1 over r, also great. And it's proportional to some known GR object. And this I is the inertia tensor of the source. Right. Now we are working to, this person, my PhD student in Paris, is now working to provide these solutions in full generality and include them into the data analysis pipeline of these. So once LISA flies in about 10 years, we will have some really nice constraints on these coefficients. Now, another thing that you can do, if you do not want to go through this rather complicated post-Newtonian expansion, is to do a direct integration. To do that, let's assume that I have a smooth source. No point particles, just a smooth source that generates my gravitational waves. And then I can start. This is just a different way of writing the same action I already showed you twice. So this is for linearized gravity. We're coming from exactly the same DFT. I'm just writing it in a different way. This S bar in red is my SME coefficient. And this G here, this is the double dual of the Riemann tensor in linearized gravity. Okay, then what I can do here that we showed last year in this paper is that you can find a strange coordinate transformation that will let you write the metric in a way that it looks like Minkowski, but it's not actually Minkowski. So it looks a bit like we've just contracted with a Beerbein, but that's not the case. And so basically the Einstein equation, you can write them in this way. This is rather long, but it's all just combinations of this new metric in this new bar coordinate system. And this looks very much like the Minkowski problem. So you solve this problem. I'm not going to show the details, but you solve the problem and then you transform back to original coordinates, which is possible to do just using textbook relation for these inverse retarded green function problems. And you will find this. This is the formal solution for this h mu nu. Now in the previous few slides I showed you the same equation. However, then I had some nested Green's functions, and it was an 8-dimensional integral. Here, I'm just integrating over the past light cone, and this tau is the source. Again, some smooth source now. S bar is my new coefficient, and what else? Yes, I also have, instead of regular retarded time, I now have some t tilde. And instead of 1 over r, so 1 over the distance from the source, I have 1 over some r tilde. And these are modified retarded time and distance, and they also contain these new coefficients S bar. So what happens is that I can solve this rather easily, but as a penalty, not only does the time I evaluate that depend on local Lorentz symmetry, but also the distance between the source and the detector. And I can depict this in this way. This is just a 1D light cone, but you can also do this easily with a 2D light cone, and then you have some kind of squeezed light cone you can see in 3 dimensions. And so in 1 dimension, I've just rotated it. And here on the right, you can see that if I'm sitting here and I'm looking at gravitational waves are coming from here. But this is not the true location of the source. The true location of the source is here. And the distance between them is somehow proportional to local Lorentz violation. So please remember that this coefficient is very small. It is at the most 10 to the minus 16. And so any discrepancy in the location is going to be completely swallowed by even 1 sigma error mode from Lisa or from LIGO. But anyway, in this setup, this is something that we expect. So you can ask yourself, what is the polarization content and waveforms that you get from such an effect? Well, because I only care about observations presently, then what I would do is I would just write down the Riemann tensor. So this is the Riemann spatial components of the Riemann tensor. This is how the detector will react to such a gravitational wave. So this does not tell me very much. So I'm going to project this onto some spatial basis and extract the polarizations. We can do it just like this. And you see immediately here that I have 5 polarizations. So 1, 2, 3, 4, 5. Yes, 5 polarizations. Now in a normal, generic metric theory, I can have 6. Here I find 5. However, to linear order in these new small coefficients, it's actually 4 polarizations. So this one is the plus polarization. This is the cross polarization. These 2 vector polarizations that we call yes and no polarization. And this is a scalar breathing mode. Okay, so you see immediately that not only do we have extra polarizations, but the standard plus and cross are modified. In here you have different combinations of S bar, and also even at the Newtonian level, I should say, this, which is the inertia tensor of the source, is modified. So if I expand this, I, and actually expanding this would take several pages, and then I can kill some of these terms because they will be quadratic in S bar. Anyway, you can also see that none of these polarizations are dynamical degrees of freedom. They are degenerate with plus and cross. You can show this explicitly. So I do have new polarizations, but I expect them to have exactly the same frequency and phase. And this is something we're currently working out. This is published results, but the waveforms and exactly how these would manifest in LISA is something that we're writing up right now in the cosmology working group. So this will be out early next year, right? Okay, so I have some more time. So I will show some recent results that I worked out in collaboration with my PhD student in Paris. So before this talk, I asked an AI to give me a cartoon of Lorentz violation. And this is what it gave me. I mean, I think this is how surprised everybody will be if we find a signal. But before I show you these vacuum solutions that my student worked out, let me show you just very briefly what happens when you break diffeomorphism symmetry explicitly. I forgot I had this in here, so let's do that quickly. In the first action that I showed you, we had some coefficient which was proportional to the Riemann tensor. Now, this term, and those two terms together is exactly the first correction, the minimal standard model extension. And so recently we asked ourselves, what happens if I include some trace term? Now this might look trivial, but it's actually not. It's far from trivial because I have now broken diffeomorphism symmetry explicit. There are no dynamical terms of this S, U, S, and D. And therefore, thanks to these transformation properties of particle and observer symmetry, particle and observer transformations, moving an index up and down in this action changes the model. So, including this trace term, for example, is not exactly, it's definitely not the same as including a 2 tensor and lowering an index. It's also not the same as including a scalar, although this holds even in GR. And so we wrote down the most general action we could think of at mass dimension 4. Derivative expansion 2. And so, let me just very briefly show you what we found. It was actually more interesting than I originally thought. The Einstein equations are this. This is okay. And then, if I pick some subset of these coefficients that I want to look at, and I satisfy the weak field constraints that we already know, then I get an equation that looks like this. And this has an extra degree of freedom, an extra dynamical degree of freedom, governed by this equation. Now, you have no extra, you have no more information than this. There's no more constraint on this capital phi, there's nothing else. So this has to be a dynamical degree of freedom. I have no other means to suppress this capital phi, and this capital phi is some combination of these traces. Okay, so this has in the traits of the metric, you have more freedom now that you've broken diffeomorphism symmetry explicit. And we also showed that this trace degree of freedom is already ruled out. How do we do that? Well, you realize that these two equations here are exactly scalar tensor theory. It's exactly Brown-Stickey theory, which you already kind of knew because this is a scalar type interaction. And if you perform the match between our construct and scalar tensor theory, you find that this coupling constant omega, which exists in scalar tensor theory, has to be 0. And given the constraints that we have on this omega, this is 100% ruled out. Why? Because omega has to be 10 to the 6th in order for solar system data on to match Brown-Stickey, or to match this version of scalar tensor theory. So we also wanted to show this in a different way, because it's very useful to rule out these kind of models. That way we don't have to care about them again. You can also try to find the gravitational waves exactly from this new degree of freedom. And so I just linearized, and again I solved the inverse grain function problem, and I get this. Now, what is this? Here is GR, so that's fine. But this extra term is unsuppressed. There is no small coefficient that suppresses this extra polarization. Oh, sorry, the modification of an existing polarization. So this should be of the same order of magnitude as the GR plus and cross. Of course, we're not seeing this. So unless when you turn on LISA or the Einstein telescope and you see this, then you can exactly rule out this type of diffeomorphism break. So this was a useful result. And it also allowed us to go a little bit further and classify what happens to gravitational waves when you introduce these trace terms. So this was just a toy example, but let me skip this and go directly to the classification. And again, only looking at the 2 tensor, because to introduce the 4 tensor is too complicated. And so this is really what we should be looking at, the most interesting thing. So you see here that we have plus, we have cross, we have, for example, the first line here, plus, cross, we have scalar mode, and we have a longitudinal mode with a star. And the star means that this mode is degenerate with plus and cross. And if you take the electric components, for example, of S, so these two, S01, 02, you also win 2 extra vector modes, vector 1 and vector 2, and so on. And so this will allow us to rule out or constrain these type of explicit diffeomorphism violation. Okay. Now we can move to black hole solution. So this was some very basic results, and the next results, it's on archive under review, and some time ago I proposed that we can try to find some nice black hole solutions with explicit diffeomorphism breaking, and you can find some that are actually quite reasonable, and some that are less reasonable. So I will show you one, and it's quite reasonable, I would say. Now this is just a couple of slides, so I'm almost done. I will skip the model. So at the non-linearized level, you can take this action. It's very short, very simple. And then I can take some ansatz, this n and n squared f spacetime, static spherically symmetric spacetime, and I do an order by order solution again. And I do an order by order solution, and I construct the reduced action. So symmetric criticality still holds when I break diffeomorphisms, so it's perfectly fine to use the reduced action. And so I will immediately find the Schwarzschild solution for 0th order. And then I plug 0th order, I plug the Schwarzschild solution in, and I find some corrections, the Schwarzschild, which are linear in this new coefficient S. This is the rationale. And I will remind you again that index position matters when you work at this level. And we simplify a little bit. This S mu nu is a constant. In some asymptotically inertial coordinates, this S is constant. And this is one of the solutions we find. Now this is very similar to Reisner-Nordström solution. So I have one extra horizon because of this 1 over r squared. And everything is linear in this S00. Now this is just the time component of S. Okay. Now you can also show that this is the only linear correction to such a system. Because if you assume this n squared equal f, then you plug this into the equation. You find an analytical solution, which is this, and now I forgot the name of these functions. Anyway, these are special functions, and if you expand this, then you exactly find this solution to linear order in S. So it's a self-consistent solution, and all the Einstein equations are satisfied. And I will just show you immediately just a couple of consequences. You have linear corrections to Hawking temperature, to singularities, and so on, in this manner. And what happens is that at some point, actually inside the horizon, but still, this term, not this term. So these two terms are going to be dominant for some small r. And you see this by the appearance of this kind of peak. See peaks in Hawking temperature, you see peaks in, this is the Kretschmann scalar for case 1. I call this case 1. And so on. But just as in Schwarzschild, there's nothing strange happening at the Schwarzschild horizon, which is here in my coordinates. Instead, everything happens inside the horizon. Okay. Now, if you look at our paper, then you see many more non-standard things happening. This is just the simplest solution we found. So, as a final thing, we also tried to get some constraints on this S00 for exactly for this case. And so we used some data from S2 from the gravity collaboration, and S2 is the star orbiting closest to Sagittarius A star. We've been observing it since I think 1990, and it follows this very nice ellipse. And I'll just skip straight to this to the result. This is just the damped harmonic oscillator and so on. Now, in order to find the precession of the perihelion, what I want is some delta phi, some shift in the angle for every orbit. And this takes on a linear correction in terms of S00. Okay, this is what I can expect from this type of Reissner-Nordström solution. And from gravity, I know the following. This quantity F, which is the ratio of, basically the ratio of the data with the GR prediction, is about 1.1. So I already know that this is going to give me quite a poor constraint on this S00. But still, this will be the first constraint of this type, so why not? So if I just plot this is F, again FSP, and here is my new coefficient. I see that in this allowed region, S has to be something like minus 0.5 to 2. Again, very poor, especially because I've already linearized an S. So maybe I can do it a little bit better. And here on the right, you see a simulated PDF of S. Because in order to calculate this for S2 or for AGR, I need all the orbital parameters of the system, and all of those come with error bars. And so I simulate those error bars, like we sometimes do in cosmology, by just drawing mocks from a Gaussian. And if I do this 10,000 times, I arrive at the following posterior distribution. And this exactly gives me something like 0.62. Again, this is extremely weak. And of course, fully consistent with 0, but again, 14 orders of magnitude. Weaker than, for example, this constraint from the speed of gravitational waves. However, it is not so weak compared to other tests, solar system tests, classical mechanics tests, and it is one of the first constraints on explicit breaking, especially from vacuum solutions. Okay, so I'm out of time, and I'm also at the end of this talk. So I asked an AI what discovery of Lorentz violation would look like. And he gave me this very nice cartoon, although it spelled everything wrong. But so in this talk, I hopefully convinced you that this is quite a rich subject, and there's a lot of activity around the world. And when it comes to gravitational waves, and especially strong gravity environments in general, we are just scratching the surface of what we can do with this EFT. I showed you that depending on the priors, some of these LIGO events seem to favor broken symmetries. And I also told you that we are finding the same with CMB polarisations in the photon sector. We're also hard at work preparing for LISA, and we expect very good constraints from there. Then, more speculatively, I showed you that you can severely bound explicit breaking from these unsuppressed modes, gravitational wave modes. And I also showed you that hopefully we can find some reasonable looking black hole solutions in these EFD subsets. So I think that's all. So thank you very much for your attention.
Thank you very much. Thank you. Okay, we have time for questions. So please.
How much time did I have? By the way, did I?
What? Sorry.
Did I run over time?
Yes.
Or
yes,
did
yes.
I? Was I?
It's fine. Thanks.
Okay, thanks.
Can I ask a question?
Sure.
Yeah.
Okay, so the question is, can you break CPT without breaking the infinitesimal transformations, like Lorentz transformations and diff transformations, but you don't break infinitesimal ones, but you do break CPT. Is it possible?
Now let's see. The strong CPT theorem by Greenberg from 2003 states, and I have to think hard to remember the implication, which way the implication arrow goes. You can have local Lorentz symmetry breaking without CPT breaking, but you cannot break CPT symmetry without also breaking Lorentz. This is, yeah.
Okay, I also have a, thank you. I also have a question about experiments. Suppose
Yes.
you introduce symmetry breaking parameters, but there are so many of them, they have so many evidences that
Yeah, they do.
I have an impression that you can fit like any experimental data with these parameters. Is it the actual situation?
You mean that I can choose something cleverly to claim that you have symmetry breaking with data? Well, this seems to be not the case because we're not finding any signals that are at least convincingly non-zero.
Yeah,
And also, when you design this for an experiment, you choose the correct coefficients that are relevant for your experiment up to some sensitivity that you have.
Yeah, but what I mean is this: you have basically hundreds of parameters in some models, and suppose you fit all of them to fit the experimental data, and you kind of. There are so many of them, hundreds, that you can basically describe any experimental data with these parameters. So, what will be the outcome? So, can you tell something from these fits?
Well, quite often, what you find when you derive this all the way down to experimental observables is that you're not sensitive to these individual coefficients. You're sensitive to some linear combination of them. And so the job then becomes to break this degeneracy. And that's not so easy. So you have to kind of import results from other experiments, I guess, which is the beauty of an EFD. But it's not so bad as you may think, exactly because sometimes you're not sensitive to one coefficient, you're sensitive to some linear combination of 10 or 20 of them. And often we do maximum reach when we analyze data. And maximum reach means that I only consider one at a time.
Okay,
so
thanks. This answer. Thanks.
Okay, thank you.
Okay, more questions? Probably from... okay, I have probably a silly question. Is it possible, at least in principle, to distinguish between spontaneous symmetry breaking, I mean Lorentz violation, and explicit Lorentz violation?
This is a good question.
Yeah. Or
At the perturbation, you have to go to some perturbation level
sorry?
because you have to do some perturbation expansion. Gravitational waves is a perturbation expansion, but in let me see. For spontaneous breaking, these new coefficients are dynamical field, and so I have dynamical fluctuations, and I fully expect massive modes, Navier-Stokes modes, and so on. And this I do not expect in explicit breaking, because there are no dynamical fields, no extra dynamical fields. And so this is, you would have to do something like this to really distinguish between the two.
So you expect additional degrees of freedom, right?
The extra propagating degree of freedom, dynamical degree of freedom, yes,
Okay.
from spontaneous breaking.
Thank you. And also I have also silly question. You mentioned several polarization of gravitational waves, and in context of LISA. Is it possible, at least in principle, to distinguish between different polarization? I just don't know.
Yes. LISA will be sensitive to different polarizations, and this is something that LIGO, current detectors are not very sensitive to, because they were not built to be sensitive to these polarizations. But LISA will be.
Okay.
We are now actually working to find out exactly how sensitive it will be.
Well, it's very interesting. Thanks. Okay, more questions? Probably from online. Well, I do not see any questions, so let us thank the speaker again. Thank you very much, Albin.
Okay, thank you.
Thank you.
Thanks very much for listening. Okay, how do I get out of this now? Let's see.
Probably you can. Yes.
Okay, there we go.
Okay. Thanks.
Okay, so thank you very much. Okay, bye.
Bye. Слушай, ну это самый звук, я что-то звук не очень.
Честно говоря, я не понимаю, что он говорит. Не понимаю.
Очень было тяжело понимать, ну в смысле просто физически понимать тяжело было.
Очень тяжело.
Я не знаю.
Нет, эти колонки дребезжат, во-первых, во-вторых, эхо. Да?
Ну да.
И даже если бы он говорил по-русски, я бы очень плохо понимал.
Тут тяжело было, очень
Тут
тяжело.
еще
Да.
тяжелее. Так бы я его понял хотя бы.
Ну,
Хотя
наверное.
он, честно говоря, не очень хорошо рассказывал, но он не безумно плохо рассказывал.
Не, он рассказал, в принципе, можно было понять. но
Можно
блин,
было понять, если бы я сидел в наушниках.
Да,
просто
да,
не надо
перед этим самым. Может быть,
в конференции.
может быть, надо действительно-
Я понял, а как ты эту проблему будешь решать, ты ее не будешь решать.
Не буду решать.
Нужно просто выбрасывать.
ну либо да.
Вот,
Да, наверное.
к сожалению.
Ну, видимо так. То есть другого варианта нет.
Либо нет, почему?
Ставить свои колонки. В принципе, у меня есть, кстати, колонки. Я их
У
специально
меня
покупал.
тоже есть колонка.
Можно попробовать.
У меня
кстати,
дома
например.
есть колонка.
Не, я сюда покупал колонки, когда
окей.
у нас были
Окей.
эти самые, когда были проблемы. С
Просто
звуком.
обычная мобильная колонка.
Да, у меня
пойдет, я думаю.
Надо попробовать,
И
кстати.
тем более. Я,
Звук отставить.